In this tutorial, let's see how to predict housing price with Keras. This tutorial is based on the book Deep Learning with Python. The author is François Chollet. By the way, he's the creator of the Keras. Thanks him to make the examples of the book available in Jupyter Notebook. Just click in the link below to access the Python code for free from his GitHub. Let's open the Boston house price dataset. First, we import Keras, and from Keras dataset, we import Boston housing. Then we create 4 variables: train data, train targets, test data, and test targets. Let's see the train data shape. We have 404 observations and 13 variables. This is a very small dataset. The purpose is to show that neural network can be applied even in a small dataset. Let's proceed to see the test data shape. We have only 102 observations. Among 13 features or explanatory variables, let's see some examples. We have per capita crime rate, proportion of residential land zone, proportion of non-retail business, a dummy if it's closer to Charles River, and the other explanatory variables. The data has to be normalized to be used as inputs in the neural network. But first, let's see the train targets, the variable that you want to predict, that is the housing pricing. That is 15K, 42K, 50K, 14K, 12K. It looks cheap because the data is from 70s and it was not adjusted for inflation. Let's now standardize the data. Remember that the z-score is the variable x minus the mu of x, that is the mean, divided by the standard deviation of the x. Let's code it. First we create the mean. Train data mean x0. 0 is the row. That means we average over the rows. Then from the train data we subtract the mean. Now let's create the standard deviation. Train data standard deviation x0. Then we divide the train data by the standard deviation. And we do the same procedure for the test dataset. It's important to note that we create the mean, the standard deviation, based on the training dataset. We didn't use the test dataset. We applied the mean in the standard deviation of the training dataset on the test dataset. It would be a big mistake to use the information from the test dataset. We call this inside information. It would invalidate the purpose of creating the test dataset. Let's proceed to build the network. From Keras, we import models and layers. Let's define a function to build the model, then you can reuse this again and again. We choose a sequential model, that is, a feedforward neural network. That means the information flow directly from the inputs x to output y's, and there is no feedback. Let's add a layer. The initial inputs will be train data shape 1, that means the columns of the training dataset. Then we take these 13 variables and apply a nonlinear transformation, the rectified linear unit function. And then we output 64 variables or neurons. Let's add one layer with the same specifications. And the third last layer has no activation function. It just outputs a linear scalar. That would be the price of the house. See that the model is smaller if only 3 layers and few neurons. The purpose is to decrease the complexity and avoid overfitting. Let's compile the model and choose the optimizer root mean square propagation that's typical from the regression problem. And for the loss function, we choose mean square error. And for metrics, we choose mean absolute error. And why we choose mean absolute error? Because it's easy to interpret. For example, if you get the number 2, that means you are off 2k. Because you have a small data set, let's apply k-fold cross-validation. Let's do a quick review about cross-validation. In the fold 1, let's break the data set in 3 partitions. 1/3 of the data will be validation, and 2/3 of the rest of the data will be training dataset. Then we go and calculate the validation score. Let's proceed to fold 2. You also have 3 partitions, but because the split is at random, the validation dataset of fold 2 will be different from the fold 1. If you do this procedure 3 times, you have 3-fold validation. Let's implement the cross-validation. We import NumPy, and we pick k equal 4. That means we split the dataset in 4 partitions. Then we divide our partition by 4. That means each partition has the same sample size. Let's do 500 epochs. It will take several minutes. And let's create the variable all mean absolute error histories to save all the results. Remember, we pick K4 and epoch 500. Here's the code for the cross-validation. This is a very generic code. If you wanna, for example, use a K10, just go in the previous slides and put K10. Now that we prepare the data for cross-validation, we can call the function build model that creates the neural network. Let's fit the model. First, we specify the data, partial train data, partial train targets, and validation data. Number of epochs is 500, that was defined before, and the batch size equal 1, and you don't want to see the results verbose equals 0. Why calculate the gradient over just one observation? Usually small batches are better than big batches. We only use big batches if you don't have computational power. It is counterintuitive, but calculates the gradient over just one observation is very noisy, but this noise it helps for non-convex optimization problem. And finally, let's save the mean absolute error, the variable that we care about. In order to avoid overfitting, let's plot the graph of mean absolute error as function of epochs. And here is the code for the graph. See that after epoch 8, the validation mean absolute error starts to increase. That suggests overfitting. Now let's see the performance on the test data. We run again the function that compiled the model. Let's fit the model. We pick train data and train targets. And based on the previous graphic, we choose epoch 8, batch size 16 is fine, and again verbose 0. And now we use the test dataset and save the results in the test mean square error score and test mean absolute error score. Let's remember the formula of mean absolute error. YY is the data, the price of the house. Y hat is the predicted value generated by the neural network. Then we average over all observations. Let's get the test mean absolute error score. It is 2.5. That means that the prediction is off by on average $2,500. It's not bad considering the small sample size and the fact that the price of the house varies from 10K to 50K. Thanks for watching. If you wanna know more about the concepts using this tutorial, you can click in the link below where you can access my other videos.